On this episode of Coding 101, TypeScript, is it for people who do JavaScript? Also, Steve Gibson drops by to give us more knowledge on CISC versus RISC and the eternal computing battle.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Coding 101 is provided by Cashfly at CACHEFLY.com.
This episode of Coding 101 is brought to you by Lynda.com. Invest in yourself for 2015. Lynda.com has thousands of courses to help you learn new tech, business, and creative skills. For a free 10-day trial, visit lynda.com/C101. That's LYNDA.com/C101. Welcome to Coding 101. It's the Twitch show where we let you into the wonderful world of the Code Monkey / Code Warrior. I'm Father Robert Ballecer, the digital Jesuit, and joining me today is our super special guest host, Mr. Lou Maresca from Microsoft. He's a senior development lead. Lou, thank you very much for coming back.
Hey, thanks for having me again, Padre.
Now, Lou, we have a nice arrangement here where you come in and you basically knock down what are some of the big developments in computer programming. And right now we're talking a little something about TypeScript. What is TypeScript?
So if you're a JavaScript programmer today, or even if you're looking to become one, sometimes it's a little daunting. And one thing it's hard to overcome with JavaScript is the fact that you can't really build, well, you can build large applications with it, but it turns out to be pretty difficult. And I don't know, Padre, have you built large applications with JavaScript before?
I mean, forgive me if I'm wrong here, but I've always used JavaScript as more of a novelty. It does fun stuff on client side, but I would never, ever, ever consider using it for something that was large scale.
Yeah, I think one of the big challenges with JavaScript is really maintaining it. And really the problem is not necessarily with the language itself. It's just really how diligent some of the developers are when they build it. And so a lot of times large applications today are built, with what they call strongly typed languages, and what that means is it allows you to kind of define the types, and then the compiler will then check them to make sure you're right. Like for instance, you can't add a string together. You have to kind of well, you can add a string together, but if you're intending to actually display a number or get a number out of it, the compiler would say no, you're passing a string into a number, and that's wrong. So it kind of forces developers to be more diligent in what they're doing.
Okay, wait, hold on. I want to clear something up right now, because there's an entire generation of programmers, myself included, for whom this conversation is completely unnecessary because I don't want to use JavaScript. And I've always been told JavaScript is insecure, JavaScript is horrible, JavaScript will lead to exploits, JavaScript can't be used in a serious application. Why go through all the time and the effort to create something that is easier to use for large-scale applications?
So I think that's kind of where the merge of these strongly typed languages are coming in to potentially JavaScript, allowing you to build in like an optionally typed language or an implicitly typed language, and then just converting that into JavaScript, and then you're really just maintaining the language that actually capable of maintaining, that can be run through tools and IDEs and other compiling tools and syntax tools and so on, linters and all that stuff, that then can make it easier to maintain in the long term. Like for instance, Google has Google Web Toolkit, which allows you to program in Java, which is a strongly typed language that compiles down to JavaScript. But sometimes it requires a whole new IDE, development environment, and even sometimes new ways of thinking. But then here is where kind of TypeScript kind of jumps in. And TypeScript is really what they call a superset of JavaScript, meaning that any valid JavaScript code is also TypeScript. But TypeScript, what it does is it proves the IDE. It does analysis of type hints. It makes developers' intent clear because you can specify optional types and inferred types. You build out classes. And what this allows you to do is surface any type of bugs or issues that can basically not be found until you run JavaScript code in a real environment or in a runtime environment. So kind of where it comes in. And TypeScript integrates to like IDEs like WebStorm and Eclipse and Sublime Text and Visual Studio and Emacs and Vim and all the ones that all developers kind of like out there. And really what it adds is a support for classes and optional typing, which is verifying your type safety like integers and strings all at compile time. Basically what we used to call in some of the beginning episodes of Coding 101, what we call sanitizing your code. And it supports inheritance and generics, which is, types to be specified later, so to speak. But again, it's basically allows you, it's easily convertible between TypeScript and JavaScript. And so JavaScript developers usually sometimes easily pick it up. But again, it makes it a lot easier. It makes it more maintainable from a JavaScript perspective, from a large web application perspective.
Lou, I understand that TypeScript can actually take in existing JavaScript code. But my question is, does the programmer have to do anything to make sure that his previously JavaScript code will work with a stronger typed TypeScript compiler?
So, I mean, you could just potentially take a big blob of your existing code and shove it into TypeScript and it will work. But TypeScript has recommendations. You can actually go through their documentation, as well as even what they call a online TypeScript playground. And what it'll do is it'll show you ways to actually break apart and modularize your code. Modules and are basically like namespaces, a way to kind of group your classes and your types. It gives you ways to do that so that this way you can break up your code and make it a little bit more maintainable by large teams. Like if you want one team to work on one part and another team to work on another part. So yeah, you could just copy your existing JavaScript directly in there and boom, your way you go. But the advantage of TypeScript is not that. The advantage of TypeScript is starting to slowly move your code into modules and break it down so that you can have it easily maintained by larger groups.
I know that TypeScript was created by the same person who is largely responsible for things like C#. So of course there's going to be elements from that language in TypeScript, but could you break it down for the real computer geeks out there, for the code warriors? What are the features, the functions, the options that I have with TypeScript that I didn't have with JavaScript?
Yeah, so I mean, there are some things that you get with JavaScript that's just really tough to. So like TypeScript, there'll be like one line that you have to write to create like a module or namespace, versus it might be a little harder to do that in TypeScript. In JavaScript itself, but it supports classes and inheritance and object-oriented concepts like inheritance and optional typing. It also supports generics, which is not necessarily supported in JavaScript, which is types to be specified later that are basically instantiated when you need a specific type to be provided as a parameter. There's modules, like I said, and again, there's straight inline JavaScript. So there's very specific things that might be supported in JavaScript themselves, but they are much easier to do when you're doing them in TypeScript. And another thing too is, just a heads up, is some of the new versions of JavaScript support ECMAScript, which is basically C# or Java-like classes, which compile down to just normal JavaScript prototype chains classes. So that's important, because that means that you can just start building a whole bunch of Java-like objects and classes and inheritance, all this stuff, and then it'll just compile down to JavaScript later. And that makes it so that you really feel like you're building a large-scale application in even kind of like a strongly typed language like C# and Java.
Lou, we've got a question, or more of a statement in the chat room from Quickston UK, who says, well, look, 10 million Minecraft users can't be wrong, right? I mean, Minecraft runs with JavaScript. My question is this: now that Minecraft is owned by Microsoft, will they migrate the code over to TypeScript? And is there a reason for them to do that?
So the reason for it to do it depends on, I don't even know how big the Minecraft development org was when they were building it. And it all depends. I mean, sometimes Microsoft usually has pretty large development orgs. And so 500,000, 5,000 developers, it's sometimes really hard to maintain a JavaScript-based application. I mean, there's a project called Mozilla Shumway project, which is 170,000 lines of TypeScript, which is basically an HTML5 product that allows you to convert your Flash SWFs, your Flash files, into HTML5 versions. And they basically built it in TypeScript because they didn't want to have to go and build all this JavaScript to do it. And so I'm going to guess that if it's maintained by a large organization and they find advantage to integrating into their build system, they probably will start to slowly convert. And that's a lot of products are doing that. Even CRM is slowly converting a lot of their components to TypeScript definitions. And so it's because, again, we have a large development org and we need to be able to maintain all that code. So there is a large advantage to doing it. And there's a lot of examples online that say, hey, I used to build in JavaScript, but now I've moved to TypeScript. I've moved to Facebook's Flow or Google ActScript, which are very similar type projects out there, and they're all trying to do the same thing, make it easier for people to develop large applications.
Okay, well, maybe some of our folks are sold. If they want to start messing around with TypeScript, where should they go? Where are all the resources they can find for TypeScript?
Sure. So, I mean, the best place to go is the TypeScript language, or TypeScriptLang.org, and they have what they call a playground out there, and you can basically start playing with it. Right up front, you type in your JavaScript code on the left, and then our TypeScript code on the left, and it converts to JavaScript. Plus, there's a little drop-down box at the top. You can see it here on the screen, where you can see all the different things that TypeScript kind of adds that JavaScript makes really difficult. So you can see kind of the code on the left versus the code on the right. And again, you can code right in here and see how it actually will run and convert over, and it basically shows you how easy it is to do. But again, other IDEs, like free IDEs that you can download, will like Visual Studio Web will allow you to download it and integrate that with TypeScript, Visual Studio Express for web, and it'll allow you to use TypeScript right in there, and you can immediately try to start converting or writing JavaScript or TypeScript code and watching it convert to JavaScript right up front, right in your web application. So, I mean, encourage you to go try that out. It's actually really, really helpful, and we, like I said, a lot of large projects are starting to move to it.
Why not? You might as well give it a go, and especially if it's going to be so easy for you to use it. Now, Lou, unfortunately, when we come back, we're going to have the last episode with Steve Gibson for a while, and yeah, there's. Yeah, a little bit of a tear runs down my face. It's so much fun to have him on the show, but he's got stuff to do. He's actually got to finish up Squirrel, and then he's got to work on the next version of SpinRite. So he's a busy man. Now, he promises us that he's going to be coming back, and we're going to do a proper assembly module from start to finish, show the folks at home how they put together their own assembly programs. But before that, do you mind, Lou, if we take a break to talk about a sponsor for this episode of Coding 101?
Of course. Let's go.
Let's do that. And it's got to be Linda. We're talking about knowledge, and Linda is all about knowledge. Now, if you are a budding programmer, if you're someone who follows Coding 101 or any of the other programming resources on the internet, you know that we can't give you everything you need. We can't do it in 45 minutes a week. We can't do it even in a series that goes on for a month. You need a reference, and that's what lynda.com is all about. A place to put all the knowledge you might need so you can answer the questions you have, even if you're not in a lesson. Now, it's already February, and I got to ask you, what are you doing? We asked you way back in January to make a promise to yourself to learn more in 2015. Are you doing it? Are you doing it yet? Well, if you're not, don't worry about it, because there's a lot of people like that, and we want to give you a way to fill that New Year's resolution with lynda.com. Invest in yourself this year and learn something new with a free 10-day trial to lynda.com. Lynda.com is used by millions of people around the world and has over 4,500 courses on topics like web development, photography, visual design, and business, as well as software training like Excel, WordPress, and Photoshop. All of their courses are taught by experts, and new courses are added to the site each and every single week. Do you want to improve your job skills, to ask your boss for a raise? Or maybe you want to make yourself more marketable for your next job. Are you looking to explore a new hobby, set a new financial goal, or find a better work-life balance? Lynda.com has something for everyone. It's not just about technology. It's not just about organization training. It's really a place where you can go and find your own personal digital guru. Now, some of the courses that I recommend are Teach Kids Programming with PHP, Java Essential Training, and Up and Running with the Google Cloud Platform, which teaches you how to develop and host apps and websites, analyze data, which is big, and create a managed cloud-based database with Google Cloud. Now, we've used Lynda here in the Brick House because we're making that transition between Macs running Final Cut and Windows boxes running Premiere Pro. Now, most of our folks are professional enough that they understand that the tools are going to be the same, but every once in a while, they run into that little teeny tiny something which is just different enough to give them pause. Well, that's why we've got lynda.com for all of our editors. They can use the transcripts to find exactly what video they need to watch, exactly what section of a video they need to watch, and get back up and producing with Premiere. That's one of the powers of lynda.com. So let's do it, folks. Invest in yourself and sign up for a free 10-day trial to lynda.com by visiting lynda.com/C101. With your membership, you'll get unlimited access to every course on lynda.com, including access to your iOS and Android devices, plus new courses as they're added each week. That's lynda.com/C101 to try it free for 10 days. Go ahead. I challenge you to learn something new. You might as well learn it at lynda.com. And we thank lynda.com for their support of Coding 101. Here's my favorite part of the show, where we get to bring in our code warrior, who just happens to be Mr. Steve Gibson. Steve, thank you very much for coming back onto Coding 101.
Great to be here, Padre.
Now, the last few episodes, we've focused on your philosophy of programming. And remember, it's all about foundations. We want foundational knowledge so that you could strip away all that high-level stuff and still understand what's going on beneath. That's really your philosophy of learning, right?
Right. I think for whatever reason, I really believe that you get the best quality if you code at the lowest level that makes sense for you. But also, even if you're coding at a higher level, understanding what's going on down below really makes you a better programmer.
Right. You know, Steve, I love our audience, and they're active in our Google Plus group. They're active in the chat room right now. We've got Cosmic Ray, we've got Morty, High Tech, Dr. Morbius, Dr. Mac. All these people are here each and every single week, and it's interesting to see how passionate they get about the language they like. We had a couple of people who were saying, look, it used to be true in the old day that assembly could be faster, but now with today's current compilers and IDEs, it's just not true anymore. And I think it comes back to what you said last week, which was you find the language that you can program in, and hopefully you'll be able to figure out what goes on underneath that language.
Well, yeah, and again, as I made more clear last week, I'm not here trying to wage a religious war against higher level languages. I think they're fine for people who like them. But like an hour ago, I was writing an algorithm to quickly scan a buffer for unsafe HTML characters and convert them into the expanded safe versions. And I was able to do in 3 instructions, after counting the number of unsafe characters, I needed to, because the expansion was going to be 4 characters larger, I needed to multiply that count by 4 and add it to the original buffer size in order to create a new buffer that would be large enough to hold all of the original characters plus the translations of the unsafe ones into safe. I did that in 4 instructions. And the problem is that no compiler understands what it's coding. It's translating what the programmer has given it into equivalent instructions. But that's the difference. I'm essentially the compiler compiling assembly language.
Yeah, so Steve, it's that granular control, right? It's that the ability to really dive in and know exactly what instructions you're asking the environment to do, rather than counting on a high-level compiler to figure it out for you.
Right. Essentially, when I'm writing assembly language, I am the compiler. And I understand the problem I'm trying to solve, so I can express that in the tools available, meaning the instructions that the hardware has. The liability, I mean, the problem any compiler has is it isn't sentient, at least not today. It doesn't actually understand the problem I'm trying to solve. It's just translating the programmer's translation of their problem into the high-level language into a lower-level language. And so essentially, I'm cutting out the middleman. And again, I understand there's an absolute place for higher-level languages, but it is absolutely not the case that I can't program circles around anyone else at the assembly language level by orders of magnitude in performance.
I want to bring Lou back in here. Lou, after Steve showed us his code yesterday, and I realized that in Microsoft's assembly, I can actually use high-level commands along with my assembly code. That, by the way, that completely blew me away. I did not know that it had advanced that much. I was actually able to do Hello World, which took me forever when I was doing that in my undergraduate days, which compares very favorable to TASM, Borland's assembly module that I learned on. Do you still use assembly from time to time? I mean, it's included in your suite.
Yeah, I think that, like somebody pointed out on Google Plus, one of the powers of assembly, even in MASM today, is really the macros that you can do. So I mean, like you were saying, it makes it really easy to inline macros into the code, and then easily converts down. There's no overhead to it, like Steve was pointing out last week. So really coding in that makes it a lot more efficient. And yeah, we do it. In fact, some of the things, some of the algorithms like binary searches and stuff, we actually do in assembly in line with the C++ code, because that's a lot more efficient than sometimes some of the ways that the different libraries and other types of libraries that we use, APIs and SDKs that we use, that do those types of things. So we just guarantee that we have the performance, the raw performance that we need there.
Two people who program for a living who are both telling you that, yeah, we still use assembly. Now, Steve, let's back away from this, because we're going to save a lot of that discussion for when we actually do the assembly module. Of course, after you get done doing the million things you have to finish for Scroll and for the next version of SpinRite. But one of the questions we got a lot after the last episode, and actually in the chat room quite a bit, is they were hoping that you would bring your knowledge to the debate between RISC and CISC architecture. Now, I remember when I was an undergrad, this was huge because, of course, there was a huge gap between RISC, reduced instruction set computing, and CISC, complex instruction set computing. And CISC was the PC, it was the x86, and RISC was the Mac. Now, we know that those have come together, but I think it's still a valid debate to talk about the differences between those two types of architecture. First of all, what was CISC versus RISC?
Well, okay, so to put this in a contemporary context, I think what's interesting is that everybody has ARM-based, ARM-design processors in their mobile devices, which are crucially power-sensitive applications. Nobody, except in laptops that have had a hard time keeping themselves alive for more than a few hours until more recently, and the batteries are vastly bigger in a laptop than in a phone, for example. So even today, the ARM architecture, which is a RISC architecture, clearly has some advantages over the older CISC-style Intel architecture. So the way to think about this is to understand the history of the way things were in the beginning. As I have mentioned a couple times, once upon a time, memory was excruciatingly expensive. I mean, if you were on a desert island and had to create memory, I mean, like literally had no resources, how would you do it? And so, for example, the early pioneers back in the 40s and the 50s, even before vacuum tubes and transistors, they used relays. And you could wire up a relay so that when the coil was energized, the armature would get pulled down and it would close a contact. Well, that contact could keep the armature energized. So that means once the relay closed, it stayed closed kind of by itself. And then if you briefly interrupted the current, it would let go. And then it would, even if then you closed that interruption, it would stay off because it had already let go and the contact had opened. So there's an example of a really kludgy one-bit memory. But once upon a time, that's all we had. And boy, I tell you, when you build a computer with those and fill a room full of it, you need to wear earplugs when this thing's running, because all those relays are clacketing around in order to do the work. And I mean, that's where we began. Then we moved to tubes, where you had a small glass bottle, essentially, with a low voltage heater that was heating up a cathode in the tube in order to boil electrons off of the cathode. And you had a high voltage plate which was attracting these electrons, and in between some mesh grids. And that's what a tube was. It was, sometime, in fact, in Britain, they called them valves. And that was, from a tube, you could create an inverter where if the input was high in a little circuit, the output was low. Well, if you connect two inverters back to back, sort of in a circle, then if the input of the first one is high, the output of it will be low. And if that goes into the second one, its input is low, so its output is high. And if you hook that back around to the first one, you've got these two little inverters, and they're stable. That is, it will stay that way. Now, if you were to briefly yank the input of the first one high, then its output would go low, and the second one's output would go high, and that would come back around and remember that. So essentially, and that's called a bistable multivibrator, because it's stable in two different states. So now we have two tubes which can remember one bit. And they're quiet, but they're burning out all the time. And they're producing, because you have to boil electrons off of the cathode, they're like little heaters. In fact, the low voltage winding in there is called a heater, and they have to warm up in order to function. So we've replaced this incredibly loud clackety process with something which is at least quiet, and it's much faster, because now we're just switching electrons rather than moving metal plates up and down. But we're producing a huge amount of heat, and we have the problem that these tubes burn out. And when you've got 10,000 of them, every time you turn the computer on, some are just going to burn out. So then you go around trying to find the ones that burned out, and it takes a while to get the computer going. We moved from there to transistors, thank goodness, and did the same thing. Two transistors can be two inverters and remember one bit of data. The problem with all of that is that these are volatile, meaning if you turn the power off, you lose the state of that bistable multivibrator. It forgets. So early pioneers had to come up with a way of creating a memory that wouldn't get lost when you turn the power off, or when someone, tripped over the cord by mistake. And again, if you think, okay, now what do we have? What possibly do we have that won't forget something? And these early guys were very clever. They figured out that they could use magnetism in order to statically remember something. So what they did was they used little donuts of ferrous material to create what has now become well known almost now in lore, because no one has anymore, a so-called core memory. These little donuts were individual cores, and they could be magnetized in one direction, clockwise, or in the other direction, counterclockwise. And when you turned the power off, they would stay that way, which was just a blessing back then. Okay, so we've gone through a huge amount of work.
Steve, 1 second. First of all, I have to make a throw out, because vacuum tubes were really my first exposure to something that would become my fascination with integrated circuits. And I remember the vacuum tube testers at Radio Shack.
Yep.
And I just mentioned that because they're now going away. But that's where I would take my tubes to see if they were still good for me to experiment with. But also, I'm getting this from the chat room. Brian, if you could bring that up. Most of the chat room, hearing you talk about this, you're doing some serious face melting right now, sir. And we love it. Please more.
Okay, so now what I wanted to impress upon us is the expense of a bit of memory. It is back in those early days, memory was, first of all, it was impossible. Then it was possible with earplugs. Then it was possible with good air conditioning and a lot of patience. And so finally, we came up with a way of using magnetism to give us non-volatile memory. But in order to create a usable amount of that, we would take these little tiny cores and thread them with wires in order essentially to magnetize them and demagnetize them and sense when the polarity of magnetization reversed. So that was a plane of memory core, but even then, 4,000 of them times, for example, 12 planes of 4,000 cores was a huge amount of work to create. And once you got it done, you had 4K words of memory. I mean, nothing in current sort of standards, but that's the kind of memory they had to work with. So the point of all of this is, if memory is incredibly expensive, you have to arrange. Yeah, there's a perfect picture of it there. Exactly, beautiful little planes of core, and that's the X and Y select and the sense wire that allows you to determine when you are changing the polarity of the core.
How much memory would you think is here, Steve? And what, like one of these arrays?
Maybe 32K.
Okay.
Bits. And the other thing that's tricky about that is, in order to know what's in the core, you have to destroy it. That is, you have to write zeros to a specific core through a set of planes. And only the cores that switch from a 1 to a 0 will generate an impulse on their sense wire. But so that tells you the ones that were 1s generated that. But in the process of determining that, notice that we just had to kill it. We had to write zeros to it. So that's called destructive readout, because it destroys the data in order to get it. So that meant that every time you read something, you had to write it back in order to have it still be there again. But there was actually something rather clever that the designers took advantage of, and that was called a so-called read, modify, write. Because if you knew that you might be changing the data that you just read, for example, you were adding a value to something in memory, you could read the contents, which would destroy it, modify the contents with the result of an addition, and then write the new value back. So, these guys were like really taking advantage of everything, every benefit they had. But the point of this is, if you have essentially no memory because the memory is too bulky, a single bit is a little magnetic, one bit is a little magnetic core, and we just saw pictures of these big modules that may have 32K bits in them. What that means is that if you're going to use this memory to contain the instructions to drive a CPU, some sort of processing unit, you need the value that you're storing, the amount of information to be as great as possible. In other words, you need complex instructions. You need to be able to have a small set of bits specify something significant for the CPU to do. And if you're able to do that, then you're able to economize on the number of instructions you need. So that's one part of that. The other part is that back in those days, human programmers were still dinosaurs. Well, they weren't dinosaurs. They were newly created creatures. I'm a dinosaur because I'm still programming in that language. But programmers were actually programming in that language. So they wanted the most complex instructions too. They wanted, with a few instructions, to be able to get a lot of work done. And so there was a balance that was struck in a little bit of memory and a lot of complexity in the processor. That was good because memory was incredibly expensive and hard to come by, and so were programmers. And so you needed programmers that didn't have to write too much code in order to get a lot done. So that's complex instruction sets. I won't go into it in any further detail. We can certainly do that easily anytime in the future. What happened over time is that world changed. Memory increasingly dropped in price to the point now where, it still makes my head spin when I look at, the gigabits you can get on a little strip for $10. It's just unbelievable compared to the memory back then. It's volatile memory because it's actually stored in capacitors that tend to leak over time, which is why you have to refresh the contents continually. You have to go back and read it before the contents has had a chance to leak away to the point where you can't tell if it used to have a 1 or 0 in there. But that technology is extremely dense and thus extremely inexpensive to manufacture. So, and we have non-volatile memory in SSDs or in hard disk drives. So we sort of load the volatile memory on the fly when we boot our computers up. So the way they operate has changed over time. But mostly the amount of memory available and the expense of memory available has just dropped. And that's allowed us to create an intermediate layer, the compiler, which insulates the programmer who wants to think in sort of more abstract, larger, broad brush terms. That's insulated the programmer from what the computer is doing underneath. Programmers don't need to know that. And so those two things brought about an evolutionary change in the way computers were designed. One of the things that happened when compilers started to be created for complex instruction set computers is that when they examined the instructions that were being used, the architects of the computers discovered that the compilers weren't using a lot of them. They had built in fancy instructions that did all kinds of cool stuff. For example, the height of that was the Digital Equipment Corp, the DEC VAX architecture. There were instructions in there for doing things like managing linked lists in the machine language, which is something you normally do at the high level. The actual chip would manage linked lists and all kinds of advanced data structures, because that's sort of the direction they went in. But if a programmer didn't have an exact match for the way they wanted to link items together, then the instruction that was sitting there begging to be used for that wouldn't get used. It couldn't be used. But more importantly, the compiler turned out not to really be able to make use of these complex instructions. What they found was that it was the simple instructions that the compiler was using a lot more of rather than the complex instructions that were there. But notice also that those complex instructions cost money. It cost money in terms of silicon area in order to create them. And this was money that was being wasted because they were not being used. So all of these various pressures got people to sort of rethink the proper architecture sort of like moving forward. And it's from that rethinking that the concept of a reduced instruction set came about. The idea being that programmers who actually had to code that would just shoot themselves, because it was painful to hand code a RISC instruction. But the point was, humans weren't supposed to. That was now the proper domain of the compiler, because what a reduced instruction set meant was you could have a vastly reduced silicon size. The chip itself could be much smaller because the instructions it had could be much simpler. You didn't need all of the area, the land mass required to support all of these complex instructions. And notice the other expense of complex instructions that are not being used is they still have all their transistors there burning up power and wasting it because they're not being used. With a reduced instruction set, you're highly using the few instructions you have. So they're far more power efficient. You're not wasting power on stuff that you're not using.
Right.
So that's essentially the trade-off, and it's the reason why Intel architecture, which is classic CISC architecture, complex instruction set, which I'm still programming in assembly language, it's the reason it's had a very difficult time surviving in the mobile world. Intel can't take instructions out because that would break code. So they're sort of jammed up. They're stuck. Whereas the ARM guys were able to start from scratch, create a very elegant, very simple chip architecture, which just glided right into the mobile world without batting an eye. And they are far more power efficient than the equivalent Intel chip.
And Steve, I want to bring Lou in here because there is a very important aspect of this CISC versus RISC architecture conversation, of this philosophy that you just brought in at the end there, which is Intel's legacy is x86. It's CISC, which means it did fantastic. It dominated the desktop/laptop space. But as we've moved into this mobile world, they just can't do it. They can't bring it over. Their Atom is kind of there, but not nearly as power efficient or as program efficient as an ARM processor for mobile processors. Actually, Lou, let me ask you about that, because Microsoft has been trying to make strides in making server software that will run on ARM boxes for that very reason. You can put a lot of those in a very small space, not generate that much heat, and not waste that much power. For a programmer right now, and there's some people in the chat room who are saying, wait a minute, I don't need any of this. This is still an incredibly important distinction to know, yes?
Yeah, I think that's important to know because, it all depends on what you're trying to apply your code to. So if you want to apply your code to, Internet of Things type thing, are you going to need to be power efficient? You're going to be plugged into a battery because you're going to be sitting there for a while, or you're going to be building a large scale application that, like you said, needs to run on a server. And doesn't need a lot of CPU power and memory behind it, that kind of thing, scalability and that kind of thing. So it's really important to distinguish between the two. But you're right. I mean, nowadays, just like Steve said, there's a lot of wasted resources, and especially CPU resources. And that's kind of where some of these cloud services are coming in, like AWS and Azure, where they're saying, you know what, we're going to share the resources of these large, massive machines and make it utilized to be 80 to 90% so that we're utilizing almost all of its CPU and memory across many different users and services that people are hosting on it, so we make it more efficient and more scalable even from a monetary standpoint. But again, they're still not as power efficient as if you were to, again, run a whole scale or parallelized version of ARM processors. So, but again, ARM processors are targeted to very specific things. So it's be very difficult to move to a server to the ARM side of things. And I'm surprised that, they're even taking strides to do it, but I have heard that they have started doing that.
Steve Gibson, thank you so very much for being, again, on this episode of Coding 101. When you come back, and we're inviting you back as soon as you put away the craziness of the current development cycle over at Gibson Research, will you be able to do a full assembly module with us? I mean, from start to finish, show these young whippersnappers how it's done.
I think we should. I think it would be fun. I would enjoy it. I found that project over on Google that I talked about last week, the PEP8 project, and I like it because it's a synthetic computer, but it is cross-platform. It's free and it's available for Windows, Mac, and Linux, and I think that's crucial because that way everyone is able to look at the examples and play with the stuff that we create. And yeah, we can just go through and sort of start with the basics of bringing things from memory and adding them and putting them back in memory and messing with loops and, play with Fibonacci numbers and find primes and all that in assembly language.
Fantastic. Of course, people can always find you on Security Now every Tuesday it's 1 o'clock, yes?
Correct. And well, until next month in March. We'll be switching to 1:30.
Exactly. So we're giving Steve a little bit more time because, I mean, as you can tell, there's nothing but nuggets, gold nuggets that fly out of his brain. But you can find him there. But if you want to see what he's developing, you have to stop by grc.com, which, by the way, is a discussion in itself, how early you had to be on the internet to get a 3-letter domain. But there you're going to find SpinRite, which is, bar none, if I could only have one tool with me when I go out on a troubleshooting ticket, that's it. Because it solves hardware problems. It solves storage problems. So SpinRite, and you're going to be up to SpinRite 6. Or is this a major release coming up?
No, we're at 6.0 now, and I'll be doing 6.1, probably a 6.2 afterwards. I want to take responsibility for the fact that I haven't updated SpinRite in a decade, and things have changed in 10 years. So I'm going to make 6.1 and 6.2 free for everyone. 6.1 will no longer use the BIOS. It'll go directly to the hardware.
Nice.
And I've seen something like a 0.5 terabyte per hour performance that we were getting. I've already got the bare metal new code running, and we're benchmarking it. So that allows you to do a 4 terabyte drive in 8 hours, so overnight, which is a huge performance improvement. It'll run natively on the Mac. The only reason it doesn't now is that the Mac has a USB-esque keyboard, and so I'll be able to work with that. And then 6.2 is going to add deeper USB support. And then my plan is, depending upon what else comes up in the meantime, to do a version 7 that will do a whole bunch of things beyond what SpinRite has ever done before.
And of course, you're still working on Squirrel, which, as we know, could potentially replace passwords, change the way that we think about authentication.
It has the potential to do it. If the industry picks it up, it can work. The demo is now online and working. We're in the process of polishing it now, so I don't have links to it yet, but we'll certainly be talking about it in the future. And it is a viable, feasible, complete replacement for the whole username and password mess.
Steve Gibson, I believe that people are now saying that you are Breaking Bad Gibson, and I believe Brian actually has a little something for us to remember. You are the one who compiles. Thank you, sir, for being on Coding 101.
Thanks so much. My pleasure.
We also want to thank our super special guest host, Mr. Lou Maresca, again, senior lead for Microsoft, for being our guest co-host. Lou, could you please tell the folks at home where they can find you?
Definitely. I want gold nuggets to come out of my brain, too. You can find me on Twitter at LouMM, L-O-U-M-M, and also about me, LouMM. And, of course, check out soon lewism.com for some of my projects that are coming out. Hopefully, there'll be gold nuggets coming out of my head, too. And then, and of course, all my work during the day is at crm.dynamics.com.
Now, don't forget that you can always find the notes for every episode if you want to see the links to the stories that we talked about. And when we do the coding episodes, if you actually want to find our code examples and our assets, just go to our show page. You can find us at twit.tv/coding or code. It all goes to the same place. There you'll find our entire back catalog of episodes. This is episode 53, so we've officially done a year plus of episodes of Coding 101, and it's also a good place for you to find entire modules. So if you want to see our C# module or our PHP module or our upcoming modules on embedded programming, that's where you want to go. Also, don't forget that we have a Google Plus group. If you just go into Google Plus and look for Coding 101, you'll be able to find us. It's a great place to find out what's been going on in our community. And it's filled with experts, beginners, and intermediate programmers. So if you've got a question or an answer, go ahead and join up. Don't forget that we do this show live, soon to be live-ish. Right now we're doing it on Thursdays at 1:30 p.m., but eventually we're going to be moving in March to 2:30, the old This Week in Enterprise Tech slot, on Mondays. So be aware there's going to be a slight schedule change. And if you are watching us live, even when we're doing our pre-recordings, you could always jump into our chat room at irc.twit.tv. I want to thank everyone who makes this show possible, to Lisa and Leo for letting me do this show on the network, and also a super special thanks to my TD, Mr. Cranky Hippo himself, Brian Burnett. Brian, where can the folks find you on the Twit TV network?
They can find me on Twitter as one of the places, at cranky_hippo. Oh, yeah,
that's me.
That's yours.
That's
but if you follow me on Twitter, you might see something like this. This is kind of behind the scenes. This was in the basement just a few, like an hour ago.
Oh, that is...
I found Hypnotoad down there.
This is what happens when you let Burke into the server room.
Yeah, exactly. So, yeah, if you follow me on Twitter, you get a little behind-the-scenes stuff of a twit. There's a Scotty picture. But also, I'm doing coding C++ in school, and this is fascinating stuff. But Steve was melting my face. So I'm going to have to go back and watch it again.
A little bit of face melting is always good. Until next time, I'm Father Robert Ballecer. Oh, and by the way, Next week, we're starting our embedded programming module. So 4 episodes where we're going to be showing you how to take an Atmega chipset from Atmel, also known as the Arduino, and turn it into something useful in the real world that requires both hardware and software skills. Lou was with us. It's going to be a killer, Lou.
Yeah, I'm gonna love it. It's good stuff, man.
Yeah. And after that, I believe we've got plans for a Ruby module. So we just did our Steve Gibson super ivory tower, super theoretical segments. We're now going to get right back into the trenches with you to teach you some of the latest and greatest in programming. Until next time, I'm Father Robert Ballecer. End of line.